So we've just finished speaking about the uh, how structured streaming is operating. Let's take a look at slightly more advanced concept of how it deals with uh, time and the notion of what it means to have late arriving data. So we're going to take the same example, but now make it a bit more complex with respect to how often the word count is computed. So we're going to say now, and this is from the Spark documentation itself, so you can easily look it up yourself and read through it. But just to explain this example a bit, uh, instead of just merely computing uh, the word count at a particular time, at a particular snapshot, I now want to associate the count to happen on a window determined by the most recent 10 minutes. And this I want to slide over a period of time where the window gets reset for every 5 minutes. So what that means is um, I have my uh, base event time itself, which is the time that's embedded in the data set. Uh, in this case, 1202, 1203, etc. That's the event time, and that event time is what I want to do the windowed computation on. And then there is the time associated with when I get triggered as a compute. That's the operational time. And that operational time, for all practical purposes, should be the same as the event time, right? Because that's the notion of refreshed most recent data being looked at. So in this case, the event time and the operational time is assumed to be the same. If it's not, then we'll look at how the late arriving data scenario is handled as an extension to this example. So so in the time axis, you're plotting the event time. So it starts off at 12, and because the window slides every 5 minutes and is spanning a length of 10 minutes for me to do my aggregates, the lowest granularity that I can trigger is going to be every 5 minutes, right? So 12, 12, 5, 12, 10, 12, 15, etc. So when I trigger my job, right, my aggregation job at 12:05, I basically will have uh, 10 minutes worth of data that I want to compute my answers on. So uh, the starting of the time is 12. So basically from 12 to 12:10 is the window that I'm considering. And within that window, what is the word count, right? So in this case, the cat, dog, dog, dog example, cat 1, dog 3, and the window corresponds to 12 to 12:10. New data comes in, let's say at 12:07. Now, if I trigger at 12:10, which is the next 5 minute boundary, I now have the entire 12 to 12:10 window uh, complete, right? Which means all of the data corresponding to what happened before 12:05, before the previous trigger, and the newer data that came in after 12:05 up till 12:10, all of the data is now complete. So with that, I have the final answer corresponding to my previous 10-minute window of 12 to 12:10. The word counts cat 2, dog 3, whole 1. But notice also that I've started a new 10-minute window corresponding to 12:05 to 12:15. And in that, I've got partial data, which is this particular message. Because I don't yet see the future time, right? 12:10 to 12:15 is not seen yet. So this data, 12:05 to 12:15, uh, for which I have the word count, that's a partial word count, but the previous word count is complete. So then when I get triggered for the next 5 minutes, 5 minutes later at 12:15, I've got now uh, 12 to 12:10 data does not change because it's already complete. 12:05 to 12:15 is now complete with the new data that's come in at 12:11 and 12:13. And so I go update that data. And that's my final answer for the 12:05 to 12:15 window. And then notice that 12:10 to 12:20 is also created. So that's a new window that gets created. So in this manner, I've computed my word count for the most recent 10 minutes, and always having a sliding window of sliding the window by every 5 minutes at any point in time. Now, why is this scenario? I mean, the scenario sounds a bit convoluted, but this is actually a very common scenario that you see because um, like for instance, certain kinds of problems like fraud detection, anomaly detection, you want to be able to see that the counts or the thresholds of what you're tracking do not go beyond a certain number uh, within the most recent time. Because if it does, then that shows that something's like dramatically wrong is happening. So in those cases, the most recent time is a time window typically, and the time window is like sliding, right? And the sliding of a time window is not continuous, right? It's always discrete, like it slides every second or every minute or whatever. So so this kind of a setup is actually way more common than you think. Now let's layer some complexity on top of this. So let's see now what happens if some data arrives late, which means data that belongs to a earlier time window occurs after the time window is done. Excuse me. So let's take this example. Um, I have now data that comes at 12:11, like basically between 12:10 and 12:15, but the event time within that data is corresponding to an older time stamp, which is 12:04. So up till 12:10, the answers are similar, actually the same as the previous example that we saw. But now, because of the late arriving data, what has now happened is um, Spark does not make any assumption that the previous time windows are complete or anything like that, because it has access to the entire result table. Remember, I was talking about it as an unbounded table, and it's just snapshotting the result along with the data. So here, the data is new, uh, but the data is actually corresponding to an older timestamp. So it goes back and figures out which window it corresponds to, and that window, the word count is getting updated for dog. So that happens automatically. So the way late arriving data is handled is just, you know, completely, intuitive, and it just is taken care of natively by structured streaming itself. And that kind of a power is actually quite immense, right? You don't have to deal with maintaining your aggregates, maintaining your time windows separately. All of that is natively taken care of by structured streaming. So this uh, document is actually quite interesting, and I suggest you read through it. Uh, one of the, for instance, implications of treating a data stream as an unbounded table is you can start to do table-like computations on top of it. Like for instance, you can start to think about joining two tables, right? We spoke about the different types of joins in SQL, right? So that actually is now available to you because now if you think about an unbounded table, and I have two unbounded tables because I have two streams of data coming in, you can start to think in terms of what does it mean for both these streams to interact with each other. The other concept is about watermarking. Watermarking happens when you need to know how much of the data in the result table you need to maintain. So in this case, 1204 came much later, but I went back in time to look at the time window that 1204 corresponds to, which is 12:0 to 12:10, and went and updated that row. Now, this could mean that the late arriving data can keep occurring again and again and again at a later point in time. So if that's the case, this result table could become infinitely bigger and bigger, right? In the worst case, becoming unbounded by itself. So to control for that, because it requires memory utilization, it requires, I mean, every snapshot creates its own, memory footprint and so on. There's a concept called as watermarking. Watermarking is basically the ability, I mean, and you can tell structured streaming that I want to define a watermark based on a particular event time column, and then appropriately Spark streaming itself would prune older data sets which have gone past the watermark. So let's say, for instance, you're saying the late arriving data cannot be more than 2 days old. And if it's more than 2 days old, I'm going to ignore it, or I'll deal with it as an invalid data. Then the watermark uh, allows you to specify 2 days as the interval, and then for data which is older than 2 days, that is automatically pruned from the result table. So that way you can keep a check on how big the result table is going to be. Okay, so that's the brief introduction about structured streaming. There's actually a lot more very interesting concepts, like how do you write windowed functions, how do you write aggregate functions which now span across multiple different time windows and things like that. Those are advanced topics. You can read up on that from the documentation. Let's come back to our main problem that we were actually looking at, right? Which is exactly once semantics. How do you now guarantee that? So let's put all of these things together. So first and foremost, you need your source system to be replayable. And we saw with Kafka, let's assume Kafka is the source, right? With Kafka, the replayability is very easy because you just go back and reset the offset to a certain number and then you can read the data again. If you couple that with Kafka's transaction semantics, then you can actually get the guarantee that at least from Kafka's perspective, you're consuming and producing data is with exactly once. Some of the other sources do not provide replayability. So an example here would be um, a log file from a machine. Right? Usually a log file from a machine is like append only. Let's say, for instance, the log file is capturing the syslog entries, in which case you keep adding, the system keeps adding newer and newer entries to the syslog, and you have to keep, um, reading the appended entries. You cannot ask the log file to go back and start from the beginning again. That's a very hard thing to do for a log file. So in that case, replayability is not possible. Certain databases obviously support it. In fact, the semantics of the source data could allow you to replay because it might have a monotonically increasing number, it might have a unique key that you can use, etc. So for exactly one semantics end to end, source systems have to be replayable. The second thing is the output sync must support the idempotent writes. So this means that you should be able to not have side effects which you can't control, right? In other words, if you redo that operation, it should produce the same output without side effects which are externally visible. So if this is possible, then you can actually get exactly once. So with structured streaming, obviously structured streaming actually uh, provides the ability for you to redo certain processing in spite of failures, and you'll get the same answer again. And that's natively guaranteed based on the model that it uses of an unbounded table. So that atomicity is guaranteed, but only for certain types of sinks. So the sink here refers to where is the result table stored, right? By default, structured streaming can actually store the result table within itself. And that is your most flexible option, which can give you the atomicity. But you can also configure structured streaming to store the sink, right? The output where it writes the output basically to a system which is which might not be supporting uh, you know idempotent operations. So the example here is console, right? So let's say you're emitting an output to a console, or you're emitting an output to an external system through, let's say, email, right? Email or a notification. In that setup, uh, if you redo an operation, even though structured streaming will guarantee will actually avoid recomputing the answer because the result table is already there. The output when it writes, it cannot take back the notification that's already gone out. It cannot take back the email that's gone out. It cannot actually go back and take back the output that it's produced to the console. So in those kinds of setups, obviously atomicity is not possible, right? It's not idempotent, so it cannot guarantee exactly once. Whereas for common databases or structured streaming's own state store, um, it can actually produce idempotent writes and give you exactly once. Then there is a write-ahead log, uh, and that write-ahead log is actually a concept which is common in relational databases. But in this case, the write-ahead log keeps track of which data has been processed and reliably written to the output sync from each source. And this is within like structured streaming. So for some kind of syncs, this log can actually be used for ensuring that the entire write is atomic, right? So remember we spoke about idempotent writes. We spoke about transactions in the context of Kafka. With structured streaming, you can now get this write-ahead log as a concept and ensure that whatever you are producing as an output, you're first writing to the log and then in case if there's a failure, you come back and ensure that the log actually is uh, propagating that right to the sink, right? So that's another way to achieve atomicity. And then finally, the system uses its own local state, right? And that local state can be really, really large in size based on the watermarking, based on how how much of a time window you base your aggregations on top of. So that you'll have to pay attention to. But if you design that carefully, you'll be able to actually achieve exactly one semantics without too much of a memory footprint, too much of a resource footprint. Great. So with that, we have come to the end of this discussion on Spark, another discussion on Spark streaming for sure, but also streaming in general. So streaming, like I said, is a very, very fascinating, uh, capability. It's got lots and lots of practical applications. So we've scratched the surface in this week's lectures and in previous weeks and this week's lectures. Uh, there's, there are more nuances to it. What I've particularly found very useful when dealing with streaming is to actually practically go and uh, write the code and test it out and see what the different scenarios are um, based on your configurations. Like the output mode can be changed, the state can be changed, etc. But a lot of it is actually design, right? Because you potentially will not be able to simulate all the failures that are possible in real world, like the failure that occurs just between writing the results and writing the offsets, right? Those kinds of things are hard to simulate unless you design very carefully designed testing systems. But it's more a question of you designing from a perspective of just thinking through where the failures can happen. And the best way to do that is just to sequentially write out the logic that you're doing and blindly insert what happens if there's a failure after this step, after this step, after this step, after this step, and then you start to reason about, okay, how can things uh, react in that kind of a manner. Great, thank you. I'll close this week's lecture.